Using my typical favourite fast learning approach where we're just going to go through loads of examples, here's a whole bunch of graphs. This is the graph y equals x. It's a straight line. It goes through the origin. This is the line y equals x squared. Always, by the way, pause the video if any of them look awkward and you could have a go at just like drawing a little table of values, trying to plot it yourself, all that kind of stuff. Anyway, this is line y equals x squared. Notice it has a minimum here at the origin, or 0, 0. That's the minimum value. And it's a curve. This is the curve y equals x cubed. By the way, this is symmetrical-ish. The curve as it goes up is kind of the same as the curve as it goes down. By the way, when I draw this, I'm just going to draw it again, because a lot of people find this difficult to draw. I always start from the center, and I do that, and then I do that, because that way I can get it to be flat in the middle. This should be horizontal in the center. And depending on the exam you're doing, if you draw it like this, and it doesn't go flat, well, that's not y equals x cubed. Anyway, let's look at another one. Oh, these are the two lines, x equals 4 and y equals 4. A lot of students find this difficult. I don't find this difficult, which is not my attempt to show off. I think it's just because how I think about graphs. Other things I find difficult, but I don't find this difficult. I always think about graphs just in terms of the fundamentals of what's happening with individual points. And I just kind of look at this and I think, oh, for every point on that line, the x coordinate is 4. I'm just using the x equals 4 as an example. So obviously that's the line x equals 4, because that's true all the way along the line. So maybe that helps. That's the graph y equals 1 over x. Notice at no point y is never equal to 0 and x is never equal to 0, because you've got asymptotes here and here and here. Let's look at another one. That's the graph y equals sine x. I always remember that sine of 0 equals 1. That's how I remember that sine x, and that helps me remember then cos x looks like that. That's my personal way of remembering. Let's look at another one. Oh, that's y equals the square root of x, which makes sense because as x gets larger, y doesn't get large as fast, because say x equals 100, then y is only 10. So if that's the line y equals x, I would expect the square root of x to kind of be lower. Anyway, there goes one thought. Oh, and of course, why doesn't the graph carry on over here? Well, because you can't square root a negative number. It's not possible. That's the cube root. Oh, but this does go to the left because you can find the cube. So, for example, what's the cube root of minus 8? It's 2. So there's going to be a point somewhere here which will be minus... I meant minus 2, by the way. Oops. Which will be minus 2. No, it won't. It'll be minus 8, comma, minus 2. There you go. Hopefully that wasn't too confusing. Let's look at another one. That's the graph y equals 10 to the x. Again, I think this is really... If you're finding this awkward, pause the video, draw a little table, and maybe just put in the numbers minus 2, minus 1, 0, 1, and 2. Go on, pause it and work it out yourself, and then come back, and you'll realise it's that. And then the whole shape of the graph makes sense. It's like, oh yeah, so like when x gets really small, and when x gets negative, it just kind of gets very close to 0. And when x becomes like 1, 2, 3, 4, 5, it just balloons up and gets really big. So that makes sense. And by the way, y equals log of x, that's just the inverse of y equals 10 to the x, because they're inverse functions. So they're mirrored in the line y equals x. So that's one explanation for the reason that y equals log x looks like that. Let's not go into any more depth on that one. This is y equals x plus 5. For me, again, I'm not sure why, but I really like graphs, suits the way I think, and to me this is really obvious because I just think, well, it's staring me in the face that x equals minus 5 is a magic number here, because that makes it equal to 0. Oh yeah, look, so it goes through minus 5, 0, and then it goes up in each direction. Always looking for magic numbers which can make brackets equal to 0. This is y equals mod x. I've just managed to scribble over it. I'll just write it again. So if you're doing modulus signs, then that is where you just take the positive value. So the modulus of -3, for example, would be 3, which is why it just bounces off 0, 0, and then goes up with positive values of y again. Y is never negative, it's always the modulus of x. Let's look at another one. Yeah, if you're not used to modulus signs, don't worry about that. Maybe that's not in your syllabus or whatever. Again, if it's in your syllabus, x squared plus y squared equals 1, that is a circle. We could test that. It's really easy to test. You could put in x equals 0. That means that y squared equals 1, which means that y equals -1 or +1, which means that we can immediately plot 2 points. We can plot the point 0, 1 and 0, -1, and then similarly we can work out these 2 points as well, and you're rapidly proving that's a circle. This is interesting because you can say, well, let's find out when y is 0. That would be when x equals 0 or when x equals 3, because that would make, because you've got two things multiplied together. So if either of them is 0, x is 0, and that's how you generate these 2 points. And then you just say, well, it's, if I ignore the 3, it's kind of like y equals x squared, near enough, which means it looks like that. The way I like to explain that, and this was explained to me at my lecture at university, is imagine holding a piece of paper a long way away. It will look like y equals x squared. Only when you get very close can you see, oh, it's not exactly on the origin. Let's look at another graph. We can use the same method again. This time we go, oh, there's 3 things multiplied together, so there's 3 different ways that we could make y equal to 0, and they're all to do with the value of x. Oh, look, that's where those 3 points came from. How do we know that it looks like this? How do we know it doesn't look like this? Whereas there's loads of ways you could find out. One way is you could just put in x equals 0, and if you do that you'll end up with y equals a negative number, so that would prove it. My personal favourite is to say what happens when x gets very big. Well, here, when x gets very big, it will just be like x times x times x, which is like x cubed, which is really big. And positive, which means it must be way up here, so it's just stretching up in that direction. Maybe pause the video if you want to try and prove this one, or let's just look at it anyway. You've got x equals 10, x equals 5, and x equals 0 as the 3 key numbers. However, 2 of them are squareds, and whenever it's a squared, it touches and bounces off. So it touches and bounces off here, touches and bounces off here, but it crosses here because it's not squared, it's just a single power. And again, I would just use the example, what if x is very big, then it's x squared times, well, x minus 5. If x is like a million, then it's like a million minus 5, so it's basically a million. And x minus 10, oh, it should have been x squared, by the way. And if x is x minus 10, if x is a million, it's basically a million. Oh, so that's x to the 5, and we know that x to the 5 is just going to get very large and positive, so it goes up there. There we go. A whole bunch of examples. Nice little bit of revision of lots of different graph shapes there. Thanks for watching.